Hello, Tess. Is this working?
Yeah.
Is it going? I don't think it's.
Yeah, we do have some.
Oh, we have sound here, but it's. Hello, good morning. All right, I think we're good. Okay, so yesterday in my first lecture, we spoke about the thermal history of the universe and how we could use the CMB to learn about the thermal history, learn about physics beyond the standard model, and in particular focused on light relics and how we measure them with the cosmic microwave background. Today, we're going to turn the clock back even farther, and we're going to look at how we can learn about the theory of inflation, the physics of inflation with observations of the cosmic microwave background. I believe it is. Yes.
Yeah.
Yeah, it's loaded. Is it loud enough to the mic?
Maybe it's not quite loud enough.
Shall we wrap it up? You can put a little closer.
Sure.
We can wrap up this a bit. All right, how's that? Okay, that seems louder. Okay, thank you. All right, good. So we're going to talk about inflation today. So we saw this same plot yesterday. This is the timeline of the universe. Just a reminder, our observations are restricted to the relatively recent cosmic past, with observations of galaxies and structure in the relatively recent universe, observation of the cosmic microwave background, which came to us from about 380,000 years after the Big Bang, and indirect sensitivity to BBN, which I didn't get to yesterday. And we're interested in learning about earlier periods through these observations. Yesterday, we talked about the thermal history, which kind of fills in this block here. Today, we're going to focus on these earliest times, what caused the initial conditions, and what generated the start of the expansion that has carried out ever since then. All right, and so in a lot of the lectures that we've already seen, there's been this thing lingering in the background that we have this spectrum of fluctuations, this spectrum of density fluctuations in particular that set the initial conditions for all of the formation of the structure and also all of the structure that we see in the cosmic microwave background. Today, we want to answer the question of why are the properties of the universe averaged on large scale so uniform, and what set up the conditions for the little density fluctuations that have seeded the structure throughout the universe. All right, and so I'll sharpen those questions as we go, but we will see that cosmic inflation does very well to answer both of these questions, and we'll start by answering the first one, and then we'll get into the second one, which will take the majority of the time. All right, I should say a lot of what I'm going to talk about, especially in the first half, is based on some excellent lecture notes written by Daniel Bauman, the Tazi lectures on inflation, which are linked from the slides if you look at the PDF, but you can also just find them on the archive. All right, so I'm going to start out with some of the classical motivation for the theory of inflation. The general statement is that the ordinary classical hot Big Bang model of cosmology is incomplete. What I mean, first of all, by the classical hot Big Bang model of cosmology is the evolution of the universe as starting from a thermal state. So we covered much of the hot Big Bang yesterday, discussing the thermal evolution in the early universe. And the hot Big Bang basically posits that that's how the universe began, in this very hot, dense thermal state. But that has problems. One of the most serious of those problems is known as the horizon problem. So in order to set this up, I need to say a little bit about what a horizon is. A particle horizon, or a horizon, is the greatest distance over which any particular event could have had an influence, either in the past or in the future. Here we're interested in the horizon in the past, the greatest distance over which things could have influenced a particular event in the history of the universe. It's very convenient when talking about causality, talking about what things could have influenced one another, to draw these so-called conformal diagrams. There's an example of a conformal diagram here. On the vertical axis is conformal time, and the horizontal axis is conformal distance. Conformal time is related to ordinary cosmic time, as shown in the leftmost equality in this expression here. The convenience of conformal time is that photons, which travel on null geodesics, make 45-degree angles on conformal diagrams. And so it's very easy to write out, to express the causal structure of some particular cosmological history using this conformal diagram, because all you need to know is that the speed limit in the universe over which signals can travel, any influence transmitted through space, travels at a maximum of the speed of light, which just corresponds to a 45-degree angle on these conformal diagrams. So this 45-degree line here is we call it the light cone, but it's the null geodesic that would be that a photon would travel throughout the universe. Now, because photons set the speed limit, this past light cone indicates the maximum distance at any given conformal time. It indicates the maximum distance from which an observer up here could have received a signal. So no physics that happened over here could have influenced the events that happened at this green point. And this is useful also when thinking about the distant past, because if I look at a different point, say down here, then the light cone, the past light cone, is again just these 45-degree angles, and it's smaller. There's a smaller region of space that could have influenced an event here. Now, this is relevant for the discussion of the classical hot Big Bang model of cosmology, because in the classical hot Big Bang model, there was a finite time in the past at which we hit a singularity, the hot Big Bang singularity. That's when the density becomes infinite or the scale factor goes to 0. And in that case, there is a definite start to the evolution of the universe, which is denoted by this horizontal line, the tau equals 0 line at the bottom here. Now, in the classical hot Big Bang model of cosmology, the universe only ever contained ordinary matter and radiation. That is the W, the equation of state defining the universe, was always greater than or equal to 0. And in such a scenario, the Hubble sphere is always growing. And the Hubble sphere is then proportional to the size of the horizon. And what this means is that we can work out by just observation of what is the temperature of the CMB, for example, and what temperatures were achieved earlier in the universe. We can work out how much conformal time existed prior to recombination between the hot Big Bang singularity and recombination, and how much conformal time there was after. And in the classical hot Big Bang scenario, there's much more conformal time after recombination than there was prior to recombination. And what that means is that the causal horizon at the time of recombination makes up only a very small fraction of the total observable universe today. And in particular, there are several, many causally disconnected regions at the surface of last scattering at recombination. In other words, if I look at 2 points on the recombination surface, which corresponds to looking at 2 different angles in the sky, those regions, as long as they were separated by more than about a degree or so, were causally disconnected. That is, there wasn't enough time in the past for any signal to have gone from one region to the other. And that means that those regions should have initial conditions that were set totally independently from one another. Okay, and that's shown in the diagram on the right. So this is basically unfolding this conformal diagram. This red line is the surface of last scattering, and the black line is where the singularity occurs in time. Remember, the singularity is a singularity in time, not in space, so that's why it appears as a sphere here. And so from that singularity, the maximum distance over which things could have traveled is just given by the radius up to the surface of last scattering, and you get many disconnected causal regions, causally disconnected regions. So different regions in the CMB sky should have been set with totally different initial conditions. And just putting numbers to that, it turns out there's about 10 to the 5 such causally disconnected regions in the standard hot Big Bang scenario. Now, this is a puzzle because we observe the CMB to be extremely uniform. Now, these days, we're most often familiar with seeing this image on the right. This is the Planck image of the temperature anisotropies in the cosmic microwave background. You might say things don't look all that uniform. Of course, statistically, things are uniform, but it's much more striking to actually go back to older data collected by Kobe And this is what you actually see when you look at the CMB before you turn up the contrast. So the top there indicates that the CMB is extremely uniform to a very, very high degree. If you look in one direction, you see some temperature. You look in a different direction, you see almost precisely the same temperature. You have to really crank up the contrast to see any deviation from that uniformity. When you crank up the contrast to about 1 part in 10 to the 3, you start to see that the CMB is actually lopsided. That lopsidedness, though, is not an intrinsic property of the cosmic microwave background. Instead, that has to do with our motion relative to the rest frame of the CMB. So when we take these observations, we're moving through the universe. And this is just the Doppler shift that shows that we're moving toward this direction and away from this direction. And it's only when you subtract this out and crank up the resolution or the contrast even more to about 1 part in 10 to the 5 that you begin to see the fluctuations which are so prominently displayed in the image on the right. Okay, so just coming back to the horizon problem, the puzzle is, why do we see the CMB to be so uniform when in the hot Big Bang scenario, we would have expected 10 to the 5 causally disconnected regions? So a naive expectation would be we should see order 1 fluctuations in each of those causally disconnected regions, unless there was some mechanism put in by hand that set the initial conditions to be uniform throughout the universe. There's another problem with the classical hot Big Bang scenario, which is called the flatness problem. In the ordinary classical hot Big Bang scenario, in which the universe was only ever filled with ordinary matter and ordinary radiation, one can make the statement that the curvature parameter, that is the deviation of the total matter density, total energy density in the universe from the critical density, that grows in time. It only ever grows in time in an ordinary classical hot Big Bang scenario. So a spatially flat universe, that is one in which the spatial hypersurfaces do not exhibit curvature, that's shown kind of here on the right. So basically there are these 3 options for the spatial curvature of our universe. It can be this spherical type geometry where the interior angles of a triangle add up to greater than 180 degrees. It can be negatively spatially curved, in which case the angles of the triangle add up to less than 180 degrees, or it can be spatially flat, in which you have ordinary flat Euclidean geometry, and the interior angles of a triangle add up to 180 degrees. We observe that the universe is very nearly exactly flat. So this is the geometrical version of it. There's also a version in terms of the expansion history that we observe that the expansion is unfolding in such a way that the density of the universe is exactly the critical density. Now, again, this is a puzzle because in a universe that contains only ordinary matter and radiation, the flat universe is an unstable fixed point of the cosmological evolution. If you have any tiny deviation from exact flatness, that deviation from flatness will grow in time in an ordinary classical hot Big Bang scenario. But we observe the universe to be very flat. And if the curvature always grows in time, and we observe the universe to be flat today, that must mean that it was extremely flat in the distant past. And so this is another puzzle about initial conditions. How can it be that the universe was so extremely flat in the early universe? So the solution to both of these classical problems, along with some other ones, like the monopole problem, which is, in fact, just as a historical note, the one that motivated Guth more than the others, though we typically today talk about the horizon problem as the most serious of these. All of these problems are solved by inflation. The basic idea of inflation is that rather than always having a growing Hubble sphere, which is what one gets when the universe is filled with only ordinary matter and radiation, inflation posits that there was a period prior to the thermal epoch where the Hubble sphere shrank. Okay, and the basic idea of this is that if the Hubble sphere is shrinking, that requires that the second derivative of the scale factor is greater than 0. In other words, that the expansion is accelerated, which also requires that there was negative pressure in the universe. Now, the advantage of this arrangement is that, unlike the initial conformal diagram we saw, a period of a shrinking Hubble sphere allows there to be much more conformal time prior to recombination. And that's the beauty of inflation with regard to the causal structure. So if you add a bunch of extra conformal time prior to the thermal state, prior to the thermal hot Big Bang. You can see just from the causal structure of this space-time that you indeed solve the horizon problem. Now, if you look at the surface of last scattering, look at recombination, what you can see is that because there's much more conformal time in the past due to this period of the shrinking Hubble sphere during inflation, that the past light cone of this point easily overlaps with the past light cone of this point, so long as this vertical distance, this conformal time, is sufficiently long compared to this conformal time. So as long as there was more conformal time during inflation than there was since recombination, the horizon problem is solved. Okay, and one can arrange for that extra conformal time simply by requiring that the Hubble sphere shrinks, which is equivalent to saying that the expansion was accelerating. Okay. This problem also solves, this solution also solves the flatness problem for the same basic reason. It actually comes down to the same mathematical requirement that as long as you had a shrinking Hubble sphere for a longer period of conformal time than there was in the ordinary classical hot Big Bang evolution, that the curvature, the spatial curvature, decreases during the shrinking Hubble sphere period, and it shrinks sufficiently that even if you started with order 1 curvature at the start of inflation, you would wind up with an exponentially suppressed curvature at the end of inflation, at this green line. And so even if it grew from that exponentially suppressed amount, it would still be smaller than we observe today. Okay, so the same mechanism solves both the horizon and the flatness problem. It also solves the monopole problem, though I won't go into that at this time. Okay. All right, so how can we arrange for such a period of accelerating expansion with a shrinking Hubble sphere? There are many ways to achieve this. One simple canonical model to have in mind is a scalar field that is uniform and whose background dynamics follow particular properties that I'll discuss next. So first of all, a scalar field is just a quantity that takes a value everywhere in space. So temperature is a scalar field. It has a numerical value everywhere in space and everywhere in time. Inflation is meant to be driven by a scalar field that is rolling in a potential. And what you can see is that the density, the energy density of a scalar field rolling in a potential is given by a kinetic term, which is related to the scalar field velocity through field space, and the potential term. So very much like a ball rolling on a hill, the energy density is related to kinetic plus potential energy. The pressure exhibited by such a scalar field is given by the difference between the kinetic term and the potential term. And so just with this fact alone, you can see an easy way to arrange for a situation with negative pressure is to imagine that the universe has an energy density that's dominated by a scalar field, whose energy density is dominated by its potential term rather than its kinetic term. So if V is much larger than 1/2 phi dot squared, the pressure will be negative. And that's exactly what we require in order to get an accelerating period of expansion. Now, the equations of motion of the scalar field are governed by classical field theory, though you can really think about almost everything to do with scalar fields rolling in a potential as just like a ball rolling down a hill, subject to a friction term. So the equation of motion is shown here. So phi double dot, which you can think about as a ball rolling down a hill, would be like x double dot, the acceleration of the ball horizontally, plus 3h phi dot. This is the Hubble friction term. So there's a term that is proportional to the field velocity, and that causes a drag. It slows down the field as it rolls. And then a force term, which is just given by the derivative of the potential with respect to the field. So in other words, the tilt of the field tells the ball to roll, tells the field to roll. Okay. And so we can arrange for an accelerating period of expansion if we have a scalar field like this, whose potential dominates over its kinetic term. Okay, and so the basic canonical picture to have in mind is this ball rolling in a hill. And then, as we will see, there are some conditions on what that hill has to look like. But the basic idea is as long as the V is greater than the 1/2 phi dot squared, then we'll have inflation. I will come back also to this part. This is how inflation ends. I'll come back and mention more about this at the end, though not much more, as you'll see. Okay, so What we require to solve the classical problems of the hot Big Bang is not just that we have a period of accelerating expansion, but that it's a sufficiently long period of accelerating expansion. We can't just have a transient epoch when things went through accelerating expansion, but it has to last a while. That is, we have to have sufficient conformal time prior to the thermal state in order to solve the problems of the classic Big Bang. And we can frame that problem in terms of what are called slow roll parameters. These will come up again and again. Their definitions are basically related to the way that the expansion unfolds. So epsilon is the first of the slow roll parameters, and it's given by minus h dot over h squared, which is the fractional change in the Hubble rate in one Hubble time. Okay, so it tells us how quickly the expansion rate evolves during inflation. If inflation is driven by a single scalar field, as we've discussed, then you can show that this is just given by 1/2 phi dot squared over h squared. And then we have the second slow roll parameter, eta, which tells us how the field accelerates in time. So it's minus phi double dot over h phi dot. It's the fractional change in the field velocity in a Hubble time. Okay, and it's also related to the change in epsilon. So it's how fast the change to the Hubble rate evolves. What we require for inflation to be successful at solving these problems is that both epsilon and eta are small or less than 1 in particular. Epsilon being small is kind of what defines inflation. So when epsilon is greater than 1, you no longer have accelerated expansion. When epsilon is less than 1, you do. Eta being less than 1 just ensures that epsilon remains smaller than 1 for a sufficient amount of time to solve these problems. Okay, and with the way we characterize what is enough accelerated expansion is often in terms of the number of e-folds of expansion defined as the log of the scale factor at the end of inflation over the start over the scale factor at the start of inflation. And without going to the numbers, I'll just tell you that if you have 60 e-folds of inflation or more, then you're guaranteed to solve these problems of the classical Big Bang, so the flatness and horizon problems. Okay, good. All right. Now, because this scalar field, when it's slowly rolling, is guaranteed to solve the problems, we can work in a regime that is very convenient. We can work in a regime where the scalar field rolls very slowly, and that allows us some simplifications in the equations, which we'll use throughout the rest. In the slow roll approximation, you can directly relate the conditions of the potential to those slow roll parameters that I defined earlier. So specifically, you can define something called epsilon v, which is the slow roll parameter based in terms of the scalar field potential, and then eta v, which is also related to the potential. Epsilon v is roughly the slope of the potential, and then eta v is the curvature of the potential, roughly speaking. And so you can see that we can translate our requirements of a sufficiently long period of accelerating expansion into conditions on the scalar field potential. Simply put, we just need a sufficiently flat potential that the scalar field can roll in to guarantee that we have a sufficiently long period of accelerating expansion. Now, the slow roll conditions allow us to simplify our equations of motion. Basically, what started as a second order differential equation simplifies to a first order differential equation. And so all the dynamics are very simple. If you know where the field is in the potential, you know its velocity and you know its evolution. And h, the expansion rate, is nearly constant and just given by h squared is 1/3 of the potential, where I've set the Planck mass to 1 in this case. Okay, so that's the basic picture. I will say in advance that this canonical picture of a single scalar field rolling in a potential is a useful one to have in mind. It's certainly not the only possibility for inflation, and we will come back to testing that toward the end of this lecture. Okay, so that's the classical dynamics of inflation. So we need some period of accelerated expansion that's sufficiently long to solve the horizon and flatness problems. Now, I should say there are many other ways to solve those horizon and flatness problems. So nothing that I've said so far should be too dramatic. You probably aren't yet very excited about the prospects of inflation. However, that scheme that I set up is much more impressive when we think about the other thing that scheme does, which is to set up the perturbations, to set up the initial conditions for the fluctuations in the universe. And as we will see, this is set by quantum fluctuations in the fields that drove inflation, and that's what we'll discuss next. Okay, So one of the very important figures that we'll see that I'll come back to again and again throughout this lecture is shown at the right here. And so we'll pick this apart piece by piece. But first, let me just say that it's very convenient, as we've heard a number of times so far in this school, that it's useful to talk about things in terms of Fourier modes rather than in terms of the quantities themselves. So we are working in perturbation theory. So for any quantity, and in particular, we're thinking about the scalar field itself or the metric. We work to first order in deviations from that uniform background. So for any quantity, we define the perturbation to that quantity as the quantity at some particular point in space minus the average quantity, the uniform quantity, the background quantity. And then we work with the Fourier modes of that quantity by taking the Fourier transform of the perturbations. Now, the advantage of this, as we've heard a number of times, is that each Fourier mode evolves independently at linear order in perturbation theory. And so there's a huge simplification to working with the Fourier modes as opposed to the fields as a function of space. I will refer very frequently to the modes at a given wave number, and this is what I mean. So I'm taking this Fourier transform, and when I talk about the modes at a particular wave number, what I mean is the fluctuation at a particular wave number k. Okay. All right. So good. So as I said, inflation you can think about as a period during which the Hubble sphere was shrinking, and then after inflation, we know that we have the standard thermal evolution and the Hubble sphere grows during that time. And so you can think about inflation in terms of setting up this portion of the diagram when the Hubble sphere shrinks as time evolves, and then the hot Big Bang is when the Hubble sphere grows. Now, throughout inflation and after inflation, any given mode is stretched along with the expansion of space. And so the wavelength or the wave number of a mode is constant on this plot. And so this blue line represents the wavelength of a particular fluctuation, and that remains constant on this type of plot. And what you can see is that that mode is going to start its life inside the horizon, by which I mean k is less than ah. And roughly what this means is that there are many oscillations of that wave mode within the horizon size, within the Hubble sphere. And then, sorry, I pointed at the wrong thing. The subhorizon means k is much greater than ah, which means that the wavelength is short compared to the Hubble sphere. And then super horizon refers to the scales like this, where the blue line is above the red line. That's where the wavelength is long compared to the Hubble sphere. And so, right, and those two regimes will be important. So any given fluctuation mode starts its life inside the horizon during inflation. It's stretched outside the Hubble sphere during inflation because the Hubble sphere shrinks while the mode grows. And then after inflation, the Hubble sphere begins growing and it catches up with the mode and the mode re-enters the horizon. Okay. All right, and so what are the modes we're talking about? What are the things that we're interested in? We are primarily interested in scalar perturbations, specifically what's called the co-moving curvature perturbation, represented by this quantity r, and the tensor perturbations, which are primordial gravitational waves. They are associated with fluctuations to the spatial part of the metric that are transverse and traceless. Okay. The reason we're focusing on these quantities is these are the two that are inevitable from any model of inflation. As we will see, you cannot avoid having either of these quantities arise during inflation. There's a whole story that I could go into with gauge choice and how we have to be careful about choosing coordinates in general relativity. Let me just summarize all of that by saying that choosing your slicing of time and choosing your foliation of space gets a little complicated. These quantities that I'm working with here, the r and this transverse traceless h, are what are known as gauge invariant quantities. So regardless of the coordinates you choose, these quantities represent real physical effects. That is not true if I'm talking about perturbations to the scalar field itself, because I can always choose a different time slicing where the scalar field is unperturbed, but I have a different definition of time in those coordinates. And so these gauge invariant quantities are a combination of that perturbation to the scalar field and the curvature, the perturbation to the metric. And then the things are actually a little bit simpler for the tensors because there's really only one definition of the transverse traceless deviation from uniformity for the spatial part of the metric. Okay, now a very important fact is that these quantities, these gauge invariant quantities are the curvature, co-moving curvature perturbation and H, the tensor perturbation, are conserved outside the horizon during and after single field inflation. Okay, so there's a lot hidden in that statement, but all I really want you to take away for now is that when the blue line is above the red line, R and H are constant, okay? And what that means is that what we can do is if we can calculate what R and H are when they exit the horizon, that tells us what they are when they re-enter the horizon much later during the classical evolution of the hot Big Bang. And so our goal is to really calculate what are R and H at horizon exit, and we can use the conservation of those quantities to make a connection with what happened during inflation to what happened much later. And this remains true despite all of the complicated details that we don't understand in the intervening epoch. So in particular, let me come back to another diagram I had here. I mentioned that there was this period of reheating, which signals the end of inflation. I said I wouldn't say a whole lot about this, and part of the reason I'm not going to say a whole lot about this is because we do not understand it. We really don't have any idea how reheating took place. What the period is, what it means by what we mean by reheating, is the time during which the energy density was transferred from the field or fields that drove inflation into the radiation that filled the universe at the start of the hot Big Bang. So it's the conversion of the stuff that drove inflation into the hot Big Bang. So reheating signals the start of the hot Big Bang. It's a transition from inflation to the thermal epoch. We have some models, some very simple models for how this might have unfolded. In this simple picture here, what's going on is that the scalar field is in the slow roll regime when it's up here. So it's dominated by Hubble friction when it's up in this flat part of the potential. As the field rolls down the potential, at some point the Hubble friction becomes negligible compared to the other pieces, and this field then begins oscillating about the bottom of the potential here. And then while it's oscillating about the bottom of the potential, it's meant to decay into the ordinary stuff of the standard model. That's a super complicated process. It becomes even more complicated if we have other dynamics going on other than just a simple single scalar field. But the advantage of working in these gauge invariant quantities, which are conserved outside the horizon, is that we can be agnostic to all of the details that occur between horizon exit for a given set of modes and horizon entry for that same set of modes. Okay. Now you'll notice here that this R dot is not written as 0, but it's written as some complicated function. This thing on the right, K squared over AH squared, that piece always goes to 0 when we're outside the horizon, because again, outside the horizon means that K is much less than AH. And so this quantity is suppressed in all models of inflation when we're outside the horizon. This other piece has a proportionality to this quantity, delta entropic pressure, so delta P En. This quantity, delta P En, is always guaranteed to vanish in single field models of inflation. Okay, so single field models of inflation always predict what are called adiabatic perturbations. And one simple way to understand what is meant here is that we've actually talked a little bit about adiabatic perturbations in some of the other lectures. Adiabatic perturbations refer to those in which all of the fluids in the system are perturbed in the same way. If there's only a single scalar degree of freedom in your problem, you're guaranteed to have only adiabatic fluctuations. And so with single scalar field inflation, there's just one scalar, the scalar field itself. And so the only way to perturb the system is to change that scalar field in a particular foliation of the space. And so there is only one perturbation to speak of, and therefore the entropic pressure must vanish. There is no difference between fields or fluids that can arise to cause this entropic pressure. That's not the case in multiple field inflation. In multiple field inflation, you have many fields, so you can have relative perturbations between the fields that drive inflation. But in single scalar field inflation, there is no entropic pressure, and so this term also vanishes. So that's a special property of single field inflation. But this condition also arises during the radiation-dominated era if the universe was only filled with a plasma that was in local thermal equilibrium with no non-zero conserved quantum numbers. In that case, the universe has just a single scalar degree of freedom, which is the temperature. If you know the temperature at some specific point in space, you know everything you need to know about the universe because you know the density of matter, dark matter, baryons, radiation, all of that kind of stuff is governed just by the temperature, okay? And so in either case, the entropic pressure vanishes and R becomes conserved. You'll notice that the difference is in multiple field inflation, this quantity does not, the R dot is not zero necessarily during inflation. But if you pass through this phase of local thermal equilibrium, then indeed the R becomes constant. We're mostly going to focus on single field inflation, for which we only need to calculate things up to horizon exit, but I'll come back and talk about multiple field inflation toward the end. Okay, so a summary of what we will try to do to make a connection between inflation and observations today is shown in this, in this diagram here. The basic idea is that fluctuations are inevitable during inflation because of quantum fluctuations in the fields and the metric during inflation. Those quantum fluctuations are produced on very, very small scales, but they naturally grow with the expansion of space. Their wavelengths are stretched with the expansion of space, while the Hubble sphere is shrinking during inflation. And so what started as very sub-horizon quantum fluctuations are stretched outside the horizon. They go through horizon exit. They are conserved while they are outside the horizon, regardless of all the complicated details that intervene. They remain conserved until horizon re-entry. And at horizon re-entry, they set the initial conditions for the subsequent evolution of the universe. And what these things represent are, like I said, co-moving curvature perturbations, which we can translate at this time of horizon re-entry into density fluctuations in the plasma, in the thermal plasma, that are adiabatic after single field inflation. We then know how to run CAMB or class to get the transfer function from those initial conditions and project it onto the observables like the CMB and large scale structure today. Okay. And so we've heard a bit about how this portion works. We're going to talk about this portion today. How do you go from quantum fluctuations to horizon exit? Okay. All right. So as I said, the fluctuations in the fields that drove inflation are inevitable. And this just has to do with quantum mechanics. So think about the standard quantum harmonic oscillator. I've shown a plot of the ground state of the quantum harmonic oscillator here. So unlike in classical physics, where the ground state is exactly determined and you know the position exactly of the ground state of a classical harmonic oscillator, there's in quantum mechanics, there's you can calculate the ground state exactly, but it doesn't give you zero uncertainty on the position or the momentum of the harmonic oscillator. So there's 0-point fluctuations in the harmonic oscillator. The same is true for the fields relevant during inflation. So you can think about this in terms of quantizing directly the curvature parameter, or you can think about it in terms of quantizing the scalar field that drives inflation. But regardless, there are necessarily quantum fluctuations in the quantity that you're looking at. Those quantum fluctuations are the things that are going to set the uncertainty in the perturbations, in the field, that will ultimately result in the curvature perturbations that become the classical outside the horizon things later on. Any scalar field that is present during inflation is subject to these quantum fluctuations. And the amplitude or the variance of those quantum fluctuations is fixed by the expansion rate. Now, this statement I didn't really justify so well here. You can think about it in a few different ways. One is in terms of this quantum harmonic oscillator. And if you work through the math, you can see that the effective mass of this quantum harmonic oscillator is associated with the expansion rate. And so you can work out that the variance is basically given by the expansion rate during inflation, which is nearly constant. And so any scalar field is subject to these quantum fluctuations. Another way to think about it is that there's a cosmological horizon during inflation. And that cosmological horizon, much like the horizon of a black hole, has quantum radiation, like Hawking radiation from a black hole. The temperature of that Hawking radiation is given by the Hubble rate because that's what sets the scale of the horizon. Regardless of how you want to think about it, any light scalar field whose mass is sufficiently below the Hubble rate during inflation is subject to a variance that is proportional to the Hubble rate squared. Okay, and good. So if you take my word for that, Then we can ask, how does that set of fluctuations in the scalar field that drives inflation translate into curvature perturbations? And here we have to go back to the diagram to show you how inflation works. The basic idea is going to be that perturbations to the scalar field change the duration of inflation. And if I change the duration of inflation, I change how much expansion took place during inflation, and that results in a curvature perturbation. So different regions that experience a different amount of expansion will exhibit curvature, which is denoted by this scalar field, by this comoving curvature perturbation R. So the basic idea is shown in any one of these diagrams, but this scalar field phi experiences quantum fluctuations. Even if it's in this vacuum state, it has quantum fluctuations that are inevitable during inflation. If I change the initial position of this scalar field as it rolls down this potential, I will change the duration of inflation in that region in space, and that translates to a curvature perturbation. And so I can put all of that together. So the curvature perturbation is just given by the Hubble rate, that is, how fast is the universe expanding during inflation, divided by the rate at which the ball rolls down the hill, phi dot, times the amount by which I deviated from the uniform background, which is equivalent to saying I've just changed the amount of time that inflation lasted, and then multiplied by the Hubble rate of that during that time. All right, and so that gives me the curvature perturbation. And so putting this all together, that is putting together the quantum fluctuations in the scalar field with the relationship between the scalar field fluctuations and this comoving curvature perturbation, I arrive at a prediction for the variance in the curvature perturbations dictated by the quantum fluctuations in the field that drove inflation. And that's given here. Now this delta R squared is the variance of the curvature perturbations. And again, so it's just the size of the quantum fluctuations times that factor that converts delta phi to R. And what I get is a prediction that the variance of the scalar field fluctuations is given by h squared over epsilon times some constants evaluated at horizon exit. And the reason I evaluate them at horizon exit is because that's when they become constant. Okay, so R becomes constant at horizon exit, and that gives me a prediction for the scalar power spectrum, the primordial power spectrum predicted by inflation. Okay, the same story that I just went through for the scalars follows through for the tensors as well. So each polarization of the tensor fluctuations or primordial gravitational waves is subject to the exact same quantum fluctuations and goes through the same evolution. The constants are a little bit different, but in the end, what you get is that each polarization of the gravitational waves is subject to the same quantum fluctuations, but there is no effect on the duration of inflation from the perturbation to the metric. And so as a result, you predict for the tensor spectrum something that just goes as h squared with some constants with no factor of epsilon. Okay, so this prediction is the statement that generically inflation predicts a spectrum of primordial gravitational waves, which is proportional to the Hubble rate during inflation squared. Okay. All right, and so again, a primordial spectrum of gravitational waves is a generic prediction of inflation. And because it's a generic prediction of inflation, if we can measure those primordial gravitational waves, that is often considered a smoking gun signature of inflation. You always get these things just as a natural consequence of the quantum fluctuations in space-time that are stretched along with the expansion of space. And I will, in the second half, report constraints on this quantity, the amplitude of these fluctuations, in terms of a quantity R, which is given as the ratio between the variance of the tensor fluctuations to the variance of the scalar fluctuations. This is a convenient way to talk about it because we measure the variance of the scalar fluctuations very well, just by measuring the anisotropies in the CMB. So that quantity is about 10 to the minus 9. And because the amplitude of the tensor fluctuations is directly proportional to h squared, and through the Friedmann equation, h squared is directly proportional to the energy density during inflation, we can relate directly R, the tensor to scalar ratio, to the potential during inflation. And so what you can see is that the potential during inflation is given by R over 0.01 to the 1/4 times 10 to the 16 GeV. So often you'll hear the phrase that a measurement of the amplitude of primordial gravitational waves would directly dictate the energy scale of inflation. This is what's meant by that statement. Okay. All right, we also predict not just the amplitude of the fluctuations, but also how they evolve with scale. That is how they tilt as we change the scale that we're looking at. And so for the scalar fluctuations, both the expansion rate and the field velocity, epsilon, change as inflation is carried out. And from these simple models of inflation, what you can expect is that the potential decreases and the field speeds up, the field speeds up in its rolling. And so what you typically expect is that epsilon is increasing while h is decreasing. And so for simple models of inflation, you predict a red tilt. You would predict that scales that are smaller have a smaller variance. And so you get this almost featureless, but slightly tilted spectrum of scalar fluctuations. On the other hand, for the tensors, the evolution is even simpler because it's proportional only to the Hubble rate. And the Hubble rate has to decrease during standard models of inflation. And so you always predict a red tilt for the tensor spectrum, specifically just related to the Hubble, the evolution of the Hubble parameter, which we called epsilon. And so all single field models of inflations, all single field slow roll models of inflation are subject to an inflationary consistency condition on the tensors, which says that the amplitude of the tensors, or the tensor to scalar ratio, is given by 16 times epsilon. And because the tilt is also related to epsilon, there's a relationship between the amplitude of scalar fluctuation, the amplitude of tensor fluctuations and the tilt. So R is always equal to minus 8 nt, which is to say that the tensor spectrum is very nearly scale invariant with a very small red tilt, with the red tilt dictated by the amplitude of those gravitational waves. Okay, so I think this is a good place to stop to take a little break. We'll come back and we'll talk about how we actually measure these things. What do we look for? But that formalism should give you some sense of what are the generic predictions of inflation, and we'll move beyond that in a second. All right, we'll be back.
Let's take a 3-4 minute, very quick bathroom break, because we've already taken some breaks and then continue.
Great, thank you. Okay, so having gone through some of the nitty-gritty details of how we produce fluctuations as quantum fluctuations during inflation, to have them stretch outside the horizon, where they become conserved, and then they map onto the classical fluctuations that set the initial conditions for the evolution of fluctuations after inflation. Now we're going to talk about how it is that we observe the signatures of inflation, in particular in the CMB, though I'll have a few comments about large-scale structure as well. All right, so Gil covered some of this yesterday, so I'll be fairly brief on this statement. But the CMB is linearly polarized, and the basic idea is that Thomson scattering in the presence of a quadrupolar anisotropy of incoming radiation produces linear polarization. So there's a little cartoon here from Wayne Hu that shows how this works. So Gil explained this a bit yesterday, but the basic idea is if you have more intense radiation coming from the left and the right, then from the top and the bottom, that preferentially jiggles this photon up and down. And so when the photons are scattered out of the page here or out of the board toward you, there's a preferential alignment of the electric field vertically. And so you get linear polarization in the presence of quadrupolar anisotropy. That naturally arises during recombination because you have density fluctuations and you have perturbations to the velocity of the plasma. And this produces a polarization of the CMB at the level of about 10%, as Gil described in a little bit more detail yesterday. Now we can characterize that linear polarization throughout a map of the sky in terms of the Stokes parameters. So the Stokes parameters are shown here. So I is just the intensity. Roughly speaking, it's the sum of the polarizations in both directions. Q is the difference of the vertical and horizontal polarizations, and U is the difference of the 45-degree polarizations. This, as Gil also pointed out, is dependent on your choice of coordinates. And so if you change what you consider to be up or down or north or south or whatever, you change the definition of Q and U. And so it's convenient to use a different definition that I'll come to in just a second. Let me also mention the other Stokes parameter that's not often discussed in the context of the CMB because it's not produced by standard physics, and that's the circular polarization, the Stokes V parameter. All right. So we're going to focus on Q and U, the linear polarization. But as I said, this is coordinate dependent, and it's also not closely tied to the physics. But E and B are closely tied to the physics and are independent of your choice of coordinates. So you can take a map of any spin 2 field on the sphere and decompose it instead of in terms of Q and U, in terms of E and B. So the E modes are meant to make you think of electric fields. These are curl free. patterns of polarization, and the B modes, meant to make you think of magnetic fields, are divergence-free. These things can be distinguished by their parity properties. So if you look at an E mode pattern in the mirror, you get back the same E mode pattern. However, if you look at a B mode pattern in the mirror, you get back the opposite sign of the B modes. All right, and so this decomposition is unique for the full sky. There's actually some complication if you look at just a portion of the sky, because there's no longer a one-to-one mapping between Q and U and E to B. But anyway, that's a technicality. Now, the importance of making this split is, as Gil also pointed out yesterday, both the scalar and tensor perturbations produce E mode polarization. However, the scalar perturbations, the density fluctuations, do not produce B mode polarization. The tensor perturbations do source B mode polarization. And because we said that this tensor fluctuation, these primordial gravitational waves, are a characteristic signature of inflation, and because the tensor fluctuations source B modes while scalars do not, a key method for probing inflation is to search for B mode polarization of the cosmic microwave background. So just to repeat that, measuring the B modes, if we can make sure that they're primordial B modes, they must have come from tensor fluctuations, and tensor fluctuations are a generic prediction of inflation. And so primordial B mode polarization to CMB is a smoking gun signature of inflation. Okay, so how do we actually measure these things? So we have discussed the temperature spectrum of the CMB, also the E mode spectrum of the CMB to some degree. These are shown with error bars from real data. What you can see, and Gil went through some of this yesterday as well, you can see that the temperature fluctuations, the temperature spectrum is very precisely measured across a really wide range of scales. The E mode polarization spectrum is quite well measured up to slightly larger scales than the T mode spectrum, and we hope to extend this to much smaller angular scales with future observations. And then down here in the dashed line is the B mode power spectrum predicted from inflation for a particular value of R. And then in the solid line is the B mode spectrum that we actually observe. And so we actually do observe the B mode spectrum. However, it's unfortunately due not to primordial gravitational waves, but rather due to lensing, which converts E mode polarization into B mode polarization. All right, so Gil will say more about this, more about lensing tomorrow, but I'll say a little bit more as we go forward. All right, so how is it that we can use these types of observations to infer what happened during inflation? All right, so the first thing we can do is let's just focus on the things that we've measured well so far, the T and E spectra. And what we see is that these spectra are very consistent with the predictions of the simple models of inflation that I've already discussed. So specifically, these spectra are consistent with adiabatic spectra of density fluctuations, which are nearly scale invariant with a very small red tilt. Okay, and that's exactly what we predicted from inflation. We also can put upper limits on this primordial B mode spectrum, even though we haven't yet detected it. If it were much larger, we would have detected it already. And so we can put upper limits on this B mode spectrum. And we can then plot these constraints. And because, as I said, for any given model of inflation, we can make definite predictions for the scalar spectrum and for the tensor spectrum, we can plot the theoretical predictions on this plane of constraints and therefore get insights into models of inflation which are viable or which are already ruled out. And so you'll often see plots like this as our CMB constraints on inflation. The vertical axis is this R, this tensor to scalar ratio. The subscript on the R here just means that this tensor to scalar ratio is evaluated at a particular scale. So the 0.002 refers to 0.002 inverse megaparsecs. And then the horizontal axis is NS, the scalar spectral tilt. Okay, we have upper limits on R, and then we have a measurement of a pretty precise measurement of NS. And as I said, the observations are consistent with a slight red tilt. If you were astute in watching earlier, the NS is defined such that if NS is 1, the spectrum is scale invariant. So NS being less than 1 means a slight red tilt. And then overplotted from on these constraints are the theoretical predictions from particular models of single field slow roll inflation, the so-called monomial models of inflation. So here is phi squared inflation. This is kind of the simplest model of inflation that you can write down. And what you can see is that simplest model of inflation is ruled out by our non-observation of primordial gravitational waves. So our upper limit on primordial gravitational waves tells us that m squared phi squared inflation is ruled out with current data. There's a bunch of other models of inflation that you can write down. All you have to do is just design a scalar field potential that obeys the conditions that we asked for, that you have a sufficiently long period of slow roll inflation. And so you can do that with different forms for the potential. So here's a linear potential, here's phi to the 2/3. And you can see that those are also slightly disfavored by the lack of observation of primordial gravitational waves, though you might say they're still consistent with the data. Now, there's a whole host of other models that you can write down. Any of those models will plot a point on this plane, and our constraints that we already have from the scalar spectra and from the non-observation of primordial gravitational waves will have something to say about models of inflation. All right. However, I've made a big point that the primordial gravitational wave spectrum is really a key to understanding inflation, really a key to understanding and nailing down the fact that inflation did take place in our past. But there are a number of challenges with going after it. So it's a key goal of future CMB experiments to measure this primordial B-mode spectrum. But there are inherent challenges in making this measurement. First of all, the signal is small. It's inherently small in the sense that this B-mode spectrum, even for relatively large values of R, is just a very, very small signal compared to the temperature fluctuations and compared to the E-mode spectrum. So the B modes are inherently small. And what that means is we have to have very precise observations of the cosmic microwave background to dig very deep. So our noise is small compared to the expected size of the signal. Compounding the problem that that the signal is inherently small, we don't know the amplitude of the primordial B mode power spectrum. We know that inflation predicts a spectrum of primordial gravitational waves, but because the scale of those primordial gravitational waves is sensitive to the scale of inflation, and there are many models of inflation, all of which would solve our classical problems, we can scale this thing up and down, still be totally consistent with the scalar spectrum, and we still don't know what the primordial gravitational wave spectrum is. In other words, I've plotted here just one specific line for R of 0.01, but I could easily write down a model of inflation for you where R is 10 to the minus 4, 10 to the minus 6, 10 to the minus 8, and it would be consistent with all our observations. Okay, so we don't know the size of the signal, but it's inherently small even in models where the tensor spectrum is considered large. Another big challenge in making this observation is that we don't get to observe the CMB unobstructed. When we look at the cosmic microwave background, we're looking through all sorts of stuff. We're looking through, in particular, polarized foregrounds from our own galaxy and also from extragalactic sources. This top plot here is a map from Planck of the polarized emission from galactic dust. And what you can see in this plot is there's no reason to expect from observations of our own galaxy that it respects this split between E modes and B modes in the way that the primordial scalar fluctuations do. In other words, the galactic foregrounds act as a source of confusion for primordial B modes because the polarized foreground emission from galaxies is some complicated mix of E modes and B modes that's sensitive to the local physics within our own galaxy. Now, if there's a saving grace here, it's that we expect that the polarized emission from galactic dust has a different spectrum in frequency than does the cosmic microwave background. So the cosmic microwave background is this very nearly perfect thermal black body with a temperature of 2.7 Kelvin. The dust in our galaxy we expect to be at a higher temperature and therefore have a different dependence on frequency than the cosmic microwave background. And so one way to clean out the foregrounds, especially from dust, is to measure the radiation at several frequencies and clean out the dust because you expect a different scaling with frequency for dust than for the CMB. A big challenge here is we don't know exactly what the frequency scaling of the dust is. It can be extremely complicated. It could be that we're looking through several different populations of dust that could be at a bunch of different temperatures. And not only that, but it can change from one patch of sky to the next. And so strategies have often focused on looking at the cleanest part of the sky we can. And so you'll notice from this polarized emission from Planck There's regions that are down here that are very blue. There are some up here that we can't actually access based on geography and stuff that are also blue. But the basic idea is we can look at very clean patches of sky and dig very deep in those cleanest patches and hope that the dust is subdominant, but also use multi-frequency observations to clean out whatever residual dust is there. The other challenge, the other inherent challenge in measuring this is that, as I showed in this plot, there's a big other lensing, there's a big other signal in B mode polarization, which is the lensing B modes. And this comes even in the presence only of scalar fluctuations. The basic idea here is that we start with E mode polarization, but light is deflected to us on its path from the surface of last scattering to our telescopes by the intervening structure. So gravitational lensing of the cosmic microwave background distorts our view of the primary CMB. This naturally converts E mode polarization into B mode polarization. You can sort of get a handle on this if you start with just E modes and you start moving these things around, literally just deflecting them on the sky. You can see how you would convert from E mode polarization into some fraction of B mode polarization. And the power spectrum of that effect is shown here. Now, this is also a big challenge. Fortunately, this one we think we have a way to deal with. So Gil will talk a little bit about how we can reconstruct the lensing deflection. And if we can actually measure the lensing deflection through statistical observations of the small scale deflections, small scale temperature and polarization, we can reverse this effect. Because we know how lensing works, we can reverse the effect and actually recover the unlensed, or a better approximation of the unlensed CMB. Good. So these are techniques that we will pursue with future observations. And we hope to get a much improved measurement, a much improved constraint or measurement of the primordial B mode spectrum. So future surveys are designed to go after this signal despite all of its challenges. And a natural question is, will we cross any thresholds? I just said that you can write down models of inflation that have vastly different values of R. So is it really worth improving it by a little bit, or are we just scraping the surface of a vast desert of possibilities? So it turns out the answer is that we do have some important thresholds that will be reached with future experiments, and in particular with CMB stage 4. So you can see here what it's anticipated to do is that CMBS4 will either achieve a measurement at 5 sigma if the signal for R is greater than 0.003, or it will set an upper limit at 0.001 at 95% confidence. And this it turns out, is a very useful threshold because it distinguishes between a broad class of models of inflation. So on this plot are shown a few more specific cases. So this blue band, this is different units than what I showed before. It's log vertical axis. So this looks different, but this is the same band of monomial potentials. So m squared, phi squared lives somewhere up here, which is already ruled out. There are some other models that are sort of important in the history of inflation. There's Higgs inflation and R squared inflation. R squared inflation is literally the first model of inflation that was ever written down, and it's still viable. And it's one of the most favored given the current data. Higgs inflation is sort of morally related to R squared inflation, but it posits that the inflaton, the field that drove inflation, is the same fundamental field that leads to electroweak symmetry breaking. Okay, so those are some specific models, but there's actually a broader class of models that will be tested with a measurement of the primordial B mode spectrum at this level. Specifically, all of the models which naturally explain the deviation from scalar spectral invariance with a characteristic scale greater than the Planck mass will be tested with this improved measurement. If we are fortunate enough to make a measurement of the primordial gravitational waves, it's hard to overstate the importance of such a measurement. It would be a direct probe of the earliest possible times that we could conceive. And what I mean by this is everything that I've discussed yesterday and today is more or less an indirect probe that comes from a period of 380,000 years after the onset of the hot Big Bang evolution. Even though we get really important sensitivity to the thermal history through measurements of N effective, those are being translated to us via the CMB. If we were to measure primordial gravitational waves, those primordial gravitational waves really would have been sourced at the very earliest times, really did come from inflation. And so we would have a window directly into these extremely early times. A measurement of these things, if we could convince ourselves that the primordial gravitational waves really came from inflation as amplification of quantum fluctuations of the vacuum, it would be evidence for the quantization of gravity, at least at the linear level. There are various ways that we can help to convince ourselves that that would be the source if we were to measure it. So for example, inflation predicts that the gravitational waves should be very Gaussian and should be red tilted in the way that I described. As I've already emphasized, the measurement of primordial gravitational waves would be very strong evidence for the paradigm of inflation. It's a generic prediction of inflation. Other alternative models that can solve the horizon and flatness problem do not predict primordial gravitational waves in the same way. It also determines the energy scale of inflation. So R is directly sensitive to the potential during inflation, which tells us the energy scale of inflation. It turns out that if it's going to be realistically measured in our lifetimes, that energy scale is very near the grand unification scale. And so that puts down a landmark for a new fundamental scale in our universe that happens to be close to a scale that's already important in particle physics, which is the grand unification scale. It also rules out a really broad class of models of inflation, the so-called small field models of inflation. This is related to something called the Lithe bound, which is just written down here. So you can write down, so as I mentioned, R is proportional to the epsilon, the slow roll parameter, which you can rewrite in terms of the evolution of the scalar field with E foldings. And what you can see is that if R is large enough to be observable, that means that the scalar field had to traverse a long distance in field space. Specifically, the field space traversed by the scalar field is given by the square root of R over 0.01. And specifically, if R is observable, that means that phi went over a distance, over what's called a super Planckian distance in field space. That's what we mean by large scale, large field models of inflation. Now, this is important also for quantum gravity because it would be, one expects that when you write down a scalar field potential, that quantum gravity should correct that potential, should modify what you thought the potential was. If it really is the case that the potential was very flat over super Planckian distances, that tells us that there's some symmetry that protects that potential over a distance where quantum gravity effects should have become important in a naive treatment. Okay, I'll leave it at that. All right, so one more topic that I'll cover very briefly before I let you all go to lunch is primordial non-gaussianity. So far I've been focused just on the 2-point statistics of the fluctuations. However, there's in principle much more information in the higher point statistics of the fluctuations. The simplest models of inflation predict pure or very nearly Gaussian scalar fluctuations, which is described entirely by the 2-point statistics, the power spectrum. And as we already said, the power spectrum is very featureless. It's almost scale invariant with a slight spectral tilt. There's really just two numbers effectively that describe that scalar, the Gaussian statistics. However, non-Gaussianity, which refers to all of the higher order statistics, so the 3 and 4 and 5-point statistics of those scalar fluctuations, in principle contain much more information. So the bispectrum, which is the Fourier transform of the 3-point correlation function, is a function of all of the vectors that make up a triangle that define the bispectrum. So assuming invariance under rotation and scaling and all that kind of stuff, this is a function of two angles, but it's a full function of those two angles as opposed to just two numbers in the power spectrum. And so there's a huge amount of information. If we could measure the bispectrum, it would tell us a huge wealth of information above and beyond what we can get from the power spectrum. And this triangle can be, so focusing specifically on the bispectrum, there are 3 different regimes where this bispectrum tells us something really characteristic about inflation. There's the equilateral shape, which is associated with 3 modes which all cross the horizon around the same time. It turns out this is closely related to the interactions of the fields that drove inflation. So in particular, derivative interactions or a non-trivial speed of sound during inflation can result in equilateral type non-Gaussianity. If you modify the initial state, so I alluded to the fact that you get vacuum fluctuations in the fields that drove inflation. If you modify that vacuum so that you weren't working from the vacuum, but working from a different state, that gives this folded shape of non-Gaussianity. And then if you have multiple fields during inflation, you're capable of producing a squeezed triangle, squeezed configuration of the bispectrum. So I'm going to highlight this so-called local or squeezed non-Gaussianity in just the last couple of slides here. So first of all, what does this thing look like? What does it do? How do we observe non-Gaussianity? So for the local shape, what you can think about is that the local type non-Gaussianity is a long wavelength modulation of small scale power. And so what I'm showing on the left here is a plot of the CMB. This was actually taken from a workshop here at the University of Michigan about over 10 years ago. This is simulations of the CMB with no non-Gaussianity in the middle here. And then this FNL parameter, which characterizes the strength of the non-Gaussianity, is shown for negative values and for positive values. It turns out it's really hard to see by eye. So you have to make this value very, very large. You have to make it like order 1 non-Gaussian for our eyes to pick up what's going on. But the large amount of statistics that's available in the CMB and also in large scale structure allows us to detect even small deviations from purely Gaussian statistics. But what you can see is that there's a large wavelength modulation of small scale power. So the map up here is patchy in the sense that in some regions you have small scale power, in other regions it's all washed out. Okay. All right, so let me very briefly tell you that all single field models of inflation predict negligible local non-Gaussianity. This is called the single field consistency condition. I'm going to give you the heuristic version of why this must be true. It's closely related to what we said about adiabatic fluctuations during inflation, during single field inflation. So long wavelength adiabatic fluctuations look locally to a local observer like just a rescaling of the coordinates. So a very long wavelength fluctuation to the curvature can be absorbed into a redefinition of your coordinates locally. And because you can do that, because you can redefine your coordinates and then make that long wavelength curvature perturbation one that's outside the horizon, make it effectively go away, it can't affect any local physics. It can't affect any of the dynamics that happen on small scales compared to the horizon. And because the local configuration of the bispectrum refers to one very long wavelength fluctuation correlated with 2 very short wavelength fluctuations, there cannot be such a correlation generated in single field models of inflation because the fluctuations are all adiabatic, and the one that exits the horizon first looks just like a coordinate rescaling for the ones that exit the horizon later, and so there can't be such a correlation that's generated during single field inflation. And so a detection of this local or squeezed configuration of non-Gaussianity would, in one fell swoop, rule out all models of single field inflation. There are multiple field models of inflation that do predict local non-Gaussianity. Just to give you some very quick examples, there's the so-called curvaton scenario. And the basic idea here is that in addition to the field that drives inflation, there's another light field that's just hanging out during inflation. It also receives quantum fluctuations in the same way that the field that drives inflation does, but it doesn't contribute to the dynamics during inflation. It's just frozen in its potential. However, after inflation, the Hubble friction goes way down, the field begins oscillating, and it can come to dominate the energy density of the universe because it redshifts more slowly than the radiation. And if that second field comes to dominate the energy density of the universe, then different regions of space underwent different histories, unlike in the case of purely adiabatic fluctuations. And this can lead to a prediction of local non-Gaussianity. It turns out that in the simplest versions of this, the prediction of FNL local is -5/4. I'm telling you that number just to give you some sense of scale when I give you the constraints in the next slide. Another scheme, another multi-field scheme, which produces local non-Gaussianity is called modulated reheating. So as I said, we know very little about how reheating unfolds, but it's this transition between scalar field dominated evolution into a thermal state. Modulated reheating is the idea that maybe there's a spectator field around that received quantum fluctuations during inflation, and which is responsible for determining the rate at which the inflaton field decays into radiation. And so if that rate is modulated by this second field, different regions of space undergo different histories, and you can violate the theorem of the single field consistency condition, and you can produce local non-Gaussianity. The simplest versions of modulated reheating predict FNL local of about 5. So again, order 1. Our current constraints on the various configurations of the bispectrum are shown here. I should say the way we measure them is basically by looking at the 3-point statistics of the cosmic microwave background, taking the Fourier transform to get the bispectrum. And so the Planck results constrain things to be very nearly Gaussian. though there's still a little bit of room in the local non-Gaussianity case for those models that I discussed earlier, the target, the theoretical threshold of interest is about order 1. And so we can constrain FNL local to be less than 1. That will really give us some convincing evidence that multi-field models of inflation, multi-field dynamics were not so important in determining our initial conditions. There are similar thresholds for FNL equilateral, also around order 1, that has to do with the dynamics of the field. And what you can see is this is the current Planck constraints. And then when we go to future CMB S4 constraints, where we have a really big improvement in sensitivity, we actually don't improve very much on these non-Gaussian constraints. And that's limited inherently by the number of modes in the cosmic microwave background. So it turns out that large scale structure is actually much more promising for future constraints on non-Gaussianity than is the CMB. There are some clever ways that you can combine the two data sets to go a little bit farther, but the basic idea is that large scale structure allows for many more modes because it's a 3-dimensional data set. And so there are many more wave vectors that you can pack into 3 dimensions than you can in the 2 dimensions of the CMB. Okay, I am keeping you for lunch, so I will stop there and I'm happy to take questions. Thanks. Oh, yes.
Thank you for the great lecture. I know you didn't want to get into all the different possible fields for inflation, but I did want to ask, all the fields you mentioned were scalar fields. Why is that the case?
Oh, yeah, good question. So yeah, so the question is, why is it always scalar fields that I was talking about for inflation? The basic idea is that if we talked about a vector field, say, that was driving inflation, that picks out a particular direction. So if there's some vector field that has some non-zero background value, that points somewhere in the sky. The same thing is true for fermions in a complicated way, and also for fermions are a little bit more complicated. For tensors, it's also true. Now, does that mean that we must have a fundamental scalar field that drives inflation? The answer to that is no. You can have more complicated dynamics as the fundamental ingredients that are driving inflation. The modern way of thinking about inflation is that instead of this fundamental scalar field rolling down a potential, there must be some effective scalar field that might come from like a condensate of some complicated self-interacting fluid, but there must be some scalar quantity which defines the length of inflation, that defines the duration of inflation. And so there's a whole formalism known as the effective field theory for inflation, and you can map the way that that works onto, in particular, FNL equilateral, because if that effective field theory becomes strongly coupled before you reach the Hubble scale, then you predict FNL equilateral of 1 or greater, which is where that threshold comes from. And so if constraining FNL equilateral to be less than 1 would tell you that that the theory of inflation is weakly coupled and therefore is well described by an effective field theory in terms of a scalar field up to the energy scale of relevance. Yes.
To that point, what energy scale is relevant, I guess, for to think of it as an effective field theory? What is the relevant cutoff in that case?
Yeah, great question. So there are a few natural scales in the problem. There's the scale of inflation itself. So H during inflation sets a scale, sets an energy scale. That one was relevant for determining what fields received quantum fluctuations and which ones were massive and could basically be ignored during the dynamics of inflation. There's another scale of relevance, which is the Planck scale, which is a scale that sets the scale of quantum gravity and gravitational effects. It turns out the relevance scale for the effective field theory is the geometric mean between those. Yeah. Yes.
Was the scalar field because of the imbalance between matter and antimatter in early universe, or it's another scalar field?
Yeah, great question. So the question is, how do we, in my cartoon here, in this phase, how do we go from inflation, which didn't have an imbalance between matter and antimatter, as far as we know, to having an abundance of matter compared to antimatter? So roughly speaking, how do we have stuff in the universe at all? So the versions of inflation that I discussed do not bear directly on that question. That you can contain the dynamics of what's called baryogenesis, where you get an abundance of matter over antimatter. You can constrain that all to the period after inflation. However, you might want to include that during inflation. You might want to say inflation set that condition, in which case you would probably need something like your inflaton, the field that drove inflation, to carry some baryon number or something like that. So that's possible. People have thought about that. But it's not at all necessary. It's not a necessary ingredient. And so from the perspective of inflation, it's basically agnostic to how you get an abundance of matter compared to antimatter. But baryogenesis falls into this category of all the complicated stuff in this regime that we don't understand. And so we're very thankful that there are quantities that are conserved outside the horizon during that complicated epoch, so that we can make a connection between inflation and what we observe today. I should say there's another way of thinking about it, which is it's unfortunate that all these quantities are conserved because they cannot give us insight into those periods we don't understand. But this, yeah, anyway, for the purpose of inflation, it's good that those things are conserved.
Thank you.
Yes. Oh, push the little.
Is that green? Sorry, I'm colorblind.
Yeah, it's great.
My question, I'm very naive about all the heavy maths to do with this, but the perturbations that you're kind of talking about, the R and the tensor perturbations, seem to be related to kind of gravity and the metric and stuff like that. And they seem to be produced in these models by sort of quantum fluctuations. And so that kind of puts a red flag in my head that you're kind of relating quantum stuff to general relativity and all of that. So what sort of ideas and assumptions do you make that kind of allow you to go between quantum and gravity situations and kind of bridge the divide there?
Yeah, great question. So this question is particularly sharp with regard to the tensor fluctuations, because in that case, we're really talking about quantum fluctuations of the space-time itself, which really requires that gravity is quantized. For the scalars, you can get away with saying maybe all of this is just that gravity is classical, but there are quantum fluctuations in the fields that drove inflation. And so there you don't actually have to confront this question of whether gravity is quantized. But this goes to the point that if we were to measure primordial gravitational waves, that would give us evidence that gravity is quantized, at least at the linear level, because if those primordial gravitational waves really came from vacuum fluctuations during inflation, it does indeed require that the quantization of gravity works the way we expect it to, at least in this linearized regime. Yeah.
Maybe, so there's a couple of more questions on Zoom, which I moved to Slack. There's a few more questions here, but minding the time, since we do have to go for lunch, we only have hour 15. Let's finish here. Thank you, Joel.
Thanks.
That's a 4 o'clock.